This is the third and final section of chapter 7, which is methods in calculus, and here we're going to be looking at the Weierstrass substitution. And basically all this is a substitution to make some integrations easier. Now, you would have already learned, hopefully, if you've done pure 2 already, integration by substitution. I'll put a link in the description. So integration by substitution is in pure 2. So I will put a link for that. And this is basically the same type of thing, but the substitution we use is t equals tan x or theta over 2, and you'll recognize this from the chapter on the t formulae. So we're basically using that to make an integration easier. Now, if we're going to do a substitution for an integration, we want to finish with this. We want dt at the end. Yeah, so we start with an integration that has dx. We're integrating with respect to x, but we're using a substitution, so we end up with some sort of function of t here, even if we started with a function of x. And if we have limits, let's call these limits x2 and x1. We'll change these limits as well so that they're in terms of t. If this is all new to you, have a look at this chapter here, have a look at the link, and that will help you. Right, so we're probably fine making a substitution from here to here, but how do we change dx to dt? Well, okay, let's see what we can do. So t equals tan x over 2. So if I differentiate that, I'll get dt dx, differentiate with respect to x, and I'll get half using the chain rule, sec squared using the formula book, x over 2. And the rest of this now is just going to be rearranging this to make dx the subject. So I'm going to multiply both sides by 2, so I get 2 dt dx equals sec squared x over 2. I really want this in terms of t, so I'm going to use the identity 1 plus tan squared x or theta equals, or is equivalent to sec squared theta, and I'll use that to change this sec squared theta to 1 plus tan squared. So I'll have 2 dt dx. It's in the wrong place, should be next to my arrow. So 2 dt dx equals 1 plus tan squared x over 2. Now, this bit here is just t squared, isn't it? If we have a look at our identity, that's just t squared. So I can write this as 2 dt dx equals 1 plus t squared, and I can multiply both sides by dx, divide both sides by 1 plus t squared, and I'll have 2 over 1 plus t squared. Okay, so unless we're asked to prove it, we can use this substitution with the dt without proof. So if a question says, right, okay, show that t equals tan over x over 2, then prove that dx equals this, then you go through these steps. Otherwise, this can be just slotted in without proof. So we want to see if we can memorize this so that we can just substitute the dx for dt straight away without having to go through all of these steps here of the proof, unless you're asked to prove it. Okay, so this question says find the integral of cosec x dx. So we will use our t formulae, the Weierstrass substitution or distribution. So t equals tan x over 2 dx is equal to 2 over 1 plus t squared dt. And we have cosec here, and cosec is 1 over sine x. That's just in case we can't remember what the t formula for cosec is. It will be 1 over, and that was 2t over 1 plus t squared. So that will be 1 plus t squared over 2t. So apart from the t being there, it's very similar to dx. So dx times by t is actually sine x. Yeah, so that's something that may help you remember this substitution here. Right, so let's go through the question. So if we want to integrate cosec x dx, that is equal to integrating 1 over sine x dx. So we'll make the substitutions. So 1 over sine x, that will be 1 plus t squared over 2t. And we substitute the dx for 2 over 1 plus t squared dt. Now I can see what will happen is these will cancel out, just leaving an integration of 2 over 2t dt, which just becomes 1 over t dt. When you integrate 1 over t, that just becomes log t. So we'll put it in modulus because it's got to be positive, plus c. Now, because we've used a substitution, we substitute back. Okay, the only time you don't substitute back is if you've changed limits and you're working out a numerical answer. So now this becomes log of the modulus of, now t was tan x over 2 plus c. There we go. So we've integrated cosec x dx. So we'll just highlight that before moving on to the next example. Okay, so we need to evaluate this integral here, which means that we're going to also be substituting the limits as well. So if we write down all of the substitutions that we're going to be using, so t is tan x over 2, dx is going to be 2 over 1 plus t squared dt. We also need to substitute the sine and cos as well. So sine x, this will be a good test to see if you've remembered these, 2t over 1 plus t squared, very similar to the dx. Here, it's just got the t in, so that's maybe a way to help you remember it. And the cos x as well. So cos x is 1 minus t squared over 1 plus t squared. Right, so they're all the substitutions. Now we also need to substitute the limits as well. So at the moment, the limits are in terms of x, and we want to turn them to limits in terms of t. So the first limit, which is x over 2, pi over 2, if we're going to turn that into a t limit, we substitute it into here. This is what links x and t. So we just do the tan of pi over 2 over 2. So tan of pi over 2 over 2, which is the same as tan pi over 4, which is 1. The other limit is pi over 3. So again, change it to a t limit, so it's going to be the tan of pi over 3 over 2. Just change x for pi over 3. And if we work that out on our calculator, we get root 3 over 3. So now we'll do all of the substitutions. So our limits now become 1 and root 3 over 3. And then we have 1 over 1 plus sine x. So that's 2t over 1 plus t squared. Minus cos x, which is 1 minus t squared over 1 plus t squared, times by dx, which we substitute for 2 over 1 plus t squared dt. Now if I was doing this question, the first thing I would do is to write this so it's got the same denominator as these, so they can all go together. So I would take that 1 and I'd write it as 1 plus t squared over 1 plus t squared. Now if I do that, this is what the integration will become. So still 1 and root 3 over 3. Then I'll multiply the tops together, so I'll have 2 there. Then at the bottom, I will have 1 plus t squared, that's from the 1, plus 2t minus 1 minus t squared, and all of that will be over 1 plus t squared. And it gets times by, well, I've moved the 2 over now, so it's just 1 over 1 plus t squared. But dividing by this is actually the same as multiplying by it, so it could go at the top there, which will mean it will cancel out with this. So these will cancel out like that. Now, not only will they cancel out, there will be some terms in that expression here that will also simplify. So let's have a look. So I've got 2 at the top. That's not going to change. So I'll just have my dt here. Then what have I got? I've got t squared and then minus t squared. So that's 2t squared. 2t squared. Let me just cross those out so that I know I've dealt with them. Then I will have plus 2t. There's no other terms to go with that. So let's cross that out. And then I'll have the 1 and minus 1, so that's just 0. So all of that just becomes this simple or much simpler expression. I can divide everything by 2. I'm going to factorize the bottom. So I will get 1 over t times by t plus 1. Now whenever you get anything like this, it's going to be partial fractions. Now I'll put a link in the description for partial fractions because that's from Pure 2. So let's use partial fractions on this. So let's do it over here. Hopefully that's enough space. So we have 1 over t times by t plus 1, which we want to write in the form a over t plus b over t plus 1. If we multiply through by the denominators and compare the numerators, we'll get 1 is equivalent to a times by t plus 1 plus b times by t. Right, so let's start by making t equal to -1. So if you make t equal to -1, that will give us 1 equals, now the a will go, and that will give us negative 1 times by b, so negative b equals 1, so in other words b equals negative 1. And then if we substitute t equal to 0, that will eliminate the b term, so I'll have 1 is equal to 0 plus 1 is just a, so a equals 1. So writing that integration, the integral as a in partial fractions, that will give me, if a is 1, so I'll have 1 over t minus 1, because b is minus 1, over t plus 1. Okay, so this is what I want to integrate with respect to t. So often when we have these fraction type things and the top is like the bottom differentiated, it becomes log when it's integrated. So the 1 over t will just become log t. Then this integrated, now if we tried log t plus 1, and what would happen is we would end up with 1 over t plus 1. We'd end up with the wrong sign. So we've got to put a negative to make it all balance. So it's got to be negative or minus log t plus 1 between these limits. Okay, so now all we need to do is to plug those limits in. We could put the logs together. It's not particularly necessary because we're just going to be substituting in fact, I might put them together. It'll just make my working a little bit more compact. So remember, when we've got a subtraction here, that means that actually these terms can be written as a division. So the natural log of t divided by t plus 1. Because we may need to give an exact answer. It may work out exact. Right, so putting those in, we'll have natural log of the first limit is 1. So it's going to be 1 over 1 plus 1. Minus natural log of second t is root 3 over 3. So root 3 over 3 divided by root 3 over 3 plus 1. And let's put that in our calculator and see what it is. That's an exact answer. Let's see what we get from our calculator. Now our calculator is not going to give us an exact answer because of these log things here. We're going to get a decimal. We can give an exact answer. So if we looked at this part here, this just becomes log half. So we've got log half minus log, and this bit will probably need our calculator to work out. That becomes log, I should have a modulus sign here, minus 1 plus root 3 over 2. Okay, now rules for log say that this is the same as log half divided by that. Let's see if we've got space to write that down. So that equals natural log of half divided by what we had up there, minus 1 plus root 3 over 3. Not sure why I did that line as big as I did, like that. And that simplifies. If you do half divided by that, we get natural log of 1 plus root 3 over 2. 1 plus root 3 over 2. I think that answer demands a bit more space up here, equals natural log of 1 plus root 3 over 2. There we go. That'll be our final answer there. You should now be able to do exercise 7c on page 158 with this Weierstrass substitution. So they're all the T formulae substitutions. This I'll recap here. And they're from a previous chapter in further pure 1. In fact, you'll find those in chapter 5. And that's the further pure 1 book, the one I'm currently working on. So we'll use this if, like, for example, we're substituting limits, and there's the other ones for sine, cos, tan, tan we've got there, and so on. Remember that you'll need to substitute everything. So everything is in terms of t, so you'll start off with something in terms of x, dx. You want to change that to something in terms of t using this substitution. If we have any limits, those limits need to be substituted as well. And when you substitute the limits, then there's no need to substitute back. So we'll just put that down. We'll just put no limits. Then you need to substitute back at the end. So whatever substitution you made for t, you need to substitute back. If you do have limits, then you don't need to substitute back. You can just evaluate. And yeah, I think the last thing is what we can substitute for dx. So unless you are asked to prove this, you can just substitute this in without further proof.